couple of notes in this question, and as I work through the question, first note is as an instructor, so, as a physics instructor, I see that this question is identical to the last in its nature. So the more that you can, and this is not a hugely different context, but the less you are confused about contexts, the likelihood is you're better physicist you're becoming. So if you see the previous problem as a cart problem and you see this as a sled problem and you think those are different, that is, in a sense, and again, it's not a criticism, it's more that it's more closely linked to novice problem solving. Expert problem solvers tend to focus in on the underlying principles that allow you to solve the problem. So in this case, it's a sled, it doesn't matter. Everything that you see in this course is governed by Newton's laws, and when we get later in the course, it'll be governed by energy principles or momentum principles. So the more you're thinking about what sort of set of rules and laws do I use to solve this particular problem, the better physicist you're becoming. And the less you get confused about whether it's a baseball, football, a car, a sled, a cart, then that's the direction you want to be moving in, because they're all governed by the same set of rules, same set of laws. The other question I had, second question. So I'm going to work through this. So I noticed, a lot of you are working away. It's also important for you to sort of figure out at what point, what sort of road did you go down that you maybe got lost and you couldn't have enough time to come back. So what kind of algebraic steps are you making that maybe if you didn't have enough time to solve this problem, try to identify the spot at which you got stopped. Because in essence, the more you identify those sort of hurdles or roadblocks and we can sort of eradicate them, then of course the better, better problem solver you become. So I've noticed that some students tend to overcomplicate a problem. And that's in a sense, again, it's not a criticism, it's something I want to point out, that you want to keep the problem solving strategy as simple as possible. So for me in this particular case, it's a Newton's laws / combined with a constant acceleration kinematics. So exactly the same context as the previous question. So your first job is to figure out what is the net force on this system of the child sled system. So free body diagram wise, I can see here, I'm not going, so they're the same forces by the, I guess it's mom and dad here, and they're pulling with, this has almost come back to that crew person question I asked several weeks ago. So they're pulling with the same force at the same angle such that their y components cancel. So I'm only going to be interested in the acceleration to the left. So that's going to be 55 times the cos at 35. And this is, so there's basically two the x components of each pulling force to the left. So there's 2 times 55 times the cos of 35 to the left. And then this sort of frictional force by the snow of 57 newtons to the right. So I'm not sure if that was a hurdle or not. Did you use the right trig function? Maybe you couldn't see from the diagram. So again, making those steps really quickly, this particular step pretty quickly. So the F net would be, I guess I'm going to just choose left to be, I guess I messed up the sign. So I did say speed here. I'm just going for a convenience. Since I know it's accelerating to the left, I'm going to make left here positive. So that's 2 times 55 newtons times the cos of 35. And it's slightly bigger than the 57. Did I do all those calculations? I did. So I think this works out to around 90.1, and then this is 33. No, 57. So you end up with a 33 Newton net force. And then the A would be just that 33 newtons divided by, again, the mass of the system. So maybe did you forget to include the 3.7? Not sure. But again, there's a small detail that you could do the whole problem and forget that 3.7. Maybe you don't see it because you're rushing or under pressure. And those are, again, but this, maybe I'm going too grand here, but those are the kind of things in your future careers, that attention to detail. Maybe you miss a tiny calculation you're administering a drug, and maybe miss a decimal point, it's going to matter more than a 5-point or 5-point physics question. I can guarantee that. So I know it means a lot to you, but the more you train your brain to like be laser focused, the less chance of like missing small details. And every sort of situation basically rewards attention to detail. There's very few that doesn't. So physics exams are no different. Anyway, get off my soapbox. You end up here with 1.45 meters per second squared. And then you're down. So once you do all of the Newton's law stuff, and now you're down to constant acceleration kinematics. You're looking for a speed after a distance. So again, fluency with equations. There's no time given. You could probably figure out the time given. No, you can't. You just got distance. You got speed. So you're going down to the v squared formula. And that's it. That kind of like fluency. So I know when I'm in a vf squared domain here, plus 2a delta x. So the final speed will be square root. Initial speed squared, so the 0.5 squared plus 2 times 1.45. Oops. I am, yeah. God. Sorry, it's been a long day. Really, really long day. VF. I am solving for VF, right? Yeah. So I'll repeat all of that. Plus 2 times 1.45 times 3. And that ends up just giving you 3 right on the button. Okay. So it's like, this is detailed, like 1 algebraic steps, count that maybe as 1 together. Net force 2, acceleration 3, speed 4. 4 maybe to 5 steps. That's a difficult problem, but that's also another thing I mentioned maybe in the first review session, is like having patience to know that this how fast piece, the actual final variable you're trying to solve for, is buried 4 to 5 algebraic steps below your first step. You're not going to, so don't. So that's why I sort of like discourage like looking for equations that have v in them. Because you're trying to solve for v. Question's not built that way. It's questions trying to build it around thinking before I can get to v, I have to do these. Maybe you start with this v. And you're like, okay, what am I missing is a, and you sort of approach it that way. And